Chris Smith joins us now. The turn of the Naked Scientist on Views and News till 12 with me, Clarence. An invitation to you to bring your question to the table. Welcome, Chris. Good to have you.
Morning.
There is a question about the Webb Alice telescope, and I know the last time we spoke about it, you were going to play catch up on it, so I don't know. But apparently it is redefining the cosmos, or maybe throwing some curveballs in terms of our understanding of the cosmos and physics as well. Is that correct?
Yeah, well, the James Webb Space Telescope has made some news this week, not once, not twice, but 3 times actually, publishing just these amazing pictures, probably back to almost the beginning of the universe. They've got some images of the evolution of the universe when it was just a few 100 million years old, looking at various clusters of galaxies and these enormous aggregations of stars, and how they begin to form sort of a meshwork or a web, which eventually informs how the universe evolves from there on in. So we've got these amazing way back in time images. They've also got this cosmic conundrum, which is that some of these galaxies from way back when, a billion years or so ago, they have black holes in the centre that are absolutely huge. And scientists and cosmologists working out how the universe evolved around that time had not anticipated that black holes would be so big so soon in the early universe. So it's always good to have a question to get your teeth into. How could these things form? How could they form where they did and be the size that they did? So that was another interesting discovery this week. And then there's a paper in the journal Nature that's just come out showing they've been gazing at a nearby star system, which is about 1,350 light years away. So it's in our cosmic neighbourhood. And what they have been able to see is the chemical imprint around this red dwarf, a fairly small, cool junior star, of the chemical called a methyl cation, or CH3+. This important carbon species has been seen in the protoplanetary disk, the material that's aggregating around the waist of the star, which will slowly condense to form planets. And why the discovery of this particular carbon compound matters is it is a building block as a source of carbon for many other much bigger, more complicated carbon-based molecules, and might therefore have a role to play in systems as they form, in seeding them with the right sorts of chemicals, perhaps even to spawn life. So we're able to now see and inform and refine our models of where these chemical species come from, when they're present during the formation of stars and planets and systems, and how they might then feed into the formation of the biosphere on those bodies that form subsequently. So 3 very interesting observations already from the James Webb Space Telescope in its first year or so of observing.
So a lot to be learnt from this little deployment of a pretty huge telescope that can see into the past, way into the past. Another question about the cosmos. If the Big Bang, if there was nothing before the Big Bang, who created nothing?
That is the question. The philosophers would say, well, the universe is 13.8 billion years old. We have evidence that the universe expanded very, very fast, very quickly, from a very, very tiny, infinitesimally small, but very, very energetic point. And since it created the universe, our universe, in the course of doing that, then before that happened, there was no universe. Doesn't mean there was no other universe, it just means that this universe didn't exist. So that's as far back really as we can go at the moment. We don't know what happened before the Big Bang. We can't go there, we can't see back to beyond that point, but we can try and get as close as possible to that point. And that's why telescopes like the James Webb, but also other instruments which are now able to read some of what people dub the afterglow of the Big Bang, and they can decode various signatures which are written into that, can give us some very tantalising glimpses into the very earliest periods of the universe. But a lot of this is just theory. We have to do models and simulations because we've got nothing to look at for something that didn't exist. So at the moment, jury's out.
Then we have a voice note in for the Naked Scientist. Let's take a listen, Joe.
Good morning, Dr. Chris Smith. A question which I'm sure lots of chefs and cooks have wondered about. When you break an egg into a pan and a piece of eggshell detaches itself and ends up in the egg white, why is it that the best way to scoop it out is using another part of the egg? the eggshell. Why does the eggshell, um, what is the affinity between the two?
Well, that's an intriguing question, and I didn't know that. And I will definitely be doing the experiment myself next time I happen to make an omelette or something, and or fry an egg, and I lose a bit of shell. I mean, I'm such a good chef that I never have that happen to me, but maybe that's just me. I wish that were true. I can only think that the reason is that the egg shell has sticking to the inside surface some of the albumin, which is the white runny stuff, protein rich, which is what becomes the egg white when it cooks. This is very viscous and very sticky, and it will therefore stick to other bits of shell, and it might be that there's enough of that on the shell, adhering to the shell, that you get some kind of surface tension effect between the bit of shell you're holding and the bit of shell you're trying to remove, and it can pluck out the bit of shell that's dropped errantly into your frying egg. But I don't know for sure. I will do the experiment myself when the opportunity presents itself, and I will give you my feedback.
That's a maths question, and it probably needs to be visible, but I don't know if you have a pen with you. Dr. Chris Smith, the chair of science at the University of Cambridge, our naked scientist on the line from the UK. So it is 6 divided by 2, and then in brackets 1 plus 2. Azuki suggests that the answer is 9. If you strictly work left to right, she says. If you solve what's in the brackets first, as we were taught, she continues, my question is, what are the real-life consequences of the two different ways of solving this maths problem, Zuki?
There is only one answer to this, which is, we call this sort of BOMDAS, or some people say BODMAS, which is brackets of multiply, divide, subtract, add, subtract. So you would evaluate the brackets first. 1 plus 2 evaluates to 3. So there's 3 in the brackets. And outside the brackets is a number 6, which means you'd multiply the 6 by the contents of the brackets and divide by 2. So you would therefore say it is 6 over 2 times the contents of the brackets, which is 3. So you've got 6 divided by 2 is 3, 3 threes are 9.
That's the only answer. 1 is not an answer.
And 1 is definitely not an answer, no.
Okay, Zuki, I know where you got that one because I found it on YouTube recently as well. And I think you've clarified for a whole lot of people in the process. Thank you, Dr. Chris Smith. Then we have this one in about deforestation in the Amazon. Let's take a listen.
Hi, Dr. Chris. JP here. A question I would like is, at the depths of the sea, like at the 13,000 feet mark where the Titanic sits, how is it possible that there are fish and stuff that swim around there and they don't get crushed by the pressure down there? Maybe you could explain that. I find that quite interesting.
Okay, we'll get back to deforestation. Let's go to that one first.
Right. Yes, you're quite right that there is life thriving at this case, 4 kilometres down. And even if you go down to the bottom of the Pacific, the Mariana Trench, and this is 12 kilometres down, you will find life down there scurrying around happy as Larry. How is it doing it where if you put a person in that situation, they would be instantly killed? The answer is that life has evolved to tolerate these very high pressures. It's not simple surviving under those pressures because the molecules that make up the proteins in your body, the way salts and other things work, do work differently under those sorts of pressures. But these creatures have evolved to have a different tension of oxygen and other gases in their bloodstream. They've evolved to have molecules that stabilize their tissues and proteins under these extremely high pressures. And this is why if you get samples of these animals and you bring them to the surface, they have the same problem on the surface that we have down at the depths, because they are not evolved to have no pressure on them compared to the 400 atmospheres that they're experiencing down where the Titanic is. So it really comes down to what you've evolved to tolerate or how you've evolved to live and survive. And these animals have adaptations that enable them to do that. For us going down there, the major problem isn't just that you've got a lot of pressure on you, because at the end of the day, if you filled your body with water, it's only because we've got lungs which are gaseous that they get crushed by the intense pressure, and this makes the volume of the lung very small, the density of the air in the lung very small, and it makes it hard to breathe. Your lungs don't work properly with that sort of density. When you're entirely filled with fluids, like a fish is, for example, it's not a problem having very high pressure on you because liquids are incompressible. But it does become a problem from the perspective that when you have those sorts of pressures, some of the molecules in your body don't work the same way as they do when you have very low levels of pressure. But if you evolve ways around that, which these animals have, then they don't have a problem surviving at those sorts of pressures.
Deforestation.
Morning, Dr. Chris. As the Amazon rainforest slowly gets stripped away piece by piece to enable farming of soybeans and all that kind of thing and agriculture, they're starting to discover that these massive cities existed in the Amazon basin. Does that mean that there is a possibility that a place like the Antarctic might have had ancient cities buried beneath all of the ice? Or did that freezing of the Antarctic, was that before humankind was around on this planet in order to build these kinds of cities and structures?
Sounds like it's raining where that question was recorded. The answer is that the Antarctic was once a very different place than it is today. And once upon a time, the temperature was balmy and tropical, and there were palm trees and lovely warm days, and there were penguins that were huge, some of them 6-8 feet tall, walking around. We've got the fossil remains of them. And the reason that there's been this dramatic turnaround is that Antarctica wasn't always isolated with a circumpolar current of freezing cold water and a vortex above it, keeping it plunged into the deep freeze. India was down where Antarctica is, and there was a land bridge up through the other continents like Australia, which meant that there was no circumpolar Southern Ocean current, so it was very warm and balmy. But this all happened 60 million plus years ago. India migrated from down where Antarctica is up to where it is now across the ocean over the last 60 million years or so, and made the Himalayas. So this is the reason that the Antarctic was very different historically. But in that time scale, that very much predates our evolution. We were still associated with the ancestor of a gorilla about 6 to 9 million years ago. So we only emerged as a humanoid sort of appearance that we have today in the last 3 to 4 million years, as Australopiths and then our own genus Homo. So we are very much recent arrivals on the scene, and all this geology and this dramatic turnaround in what Antarctica was like was in the very, very distant past, around the time when the dinosaurs were knocking around on Earth. So not in our timeline. So there were no cities on Antarctica, but there were certainly nice places to live and some very big animals that enjoyed the equivalent of a hot summer holiday on Antarctica way back when.
We're chatting to the Naked Scientist. Your calls on 021 446 0567. WhatsApp messages and voice notes on 072 567 1567. What causes ocean swell? Some days the waves are huge, and other days the sea is as flat as a lake. That's a question in for you.
Well, water is a fluid, and it's a mobile fluid, and water moves naturally around the world because of tides. It also moves because of air pressure, and if you have a low pressure, then the water will heap up because it will flow more towards an area of low pressure, meaning that you have a higher than average ocean height there. And at the same time, the surface of the water is susceptible to the effects of wind. So as the wind blows over the surface of the ocean, especially if the tide is running one way and the wind is blowing the other, then the two will act against each other, and the surface of the ocean will be pulled up and forced into waves. So when you combine that effect, a tide with low pressure and a strong wind counter to the tidal direction, you can get very big swells indeed. And people who do a lot of sailing and boating will know very well when you get wind over tide, it's going to be rough. So if you try to arrange your sailing trip or your day out or your journey to try to go out with the tide and come back with the tide and the wind, you're going to have a much nicer day than if you try to fight where wind and tide are against each other, because it will be much rougher and you're more likely to be over the side going green.
Dr. Smith, have you ever heard of the scaly foot snail? It's also known as the sea pangolin, and it lives near hydrothermal vents and can tolerate temperatures of 300 degrees Celsius. My question is, how can it survive at that temperature? And I think the bigger question is, how do you cook something that can survive?
It doesn't sound like you'd need to cook it. It sounds like it would come pre-cooked. The answer is these are extremophile organisms. In other words, organisms that tolerate and love living in extreme environments. The hydrothermal vents, when we discovered what lives there, were an amazing epiphany for scientists in the last 20, 30 years when they were able to build submersibles and go down to some of these deep black smokers, these hydrothermal systems that produce superheated water on the ocean floor, very rich in minerals and other nutrients. And of course, that affords life forms an opportunity. Because other things can't live there, you're less likely to be predated. If you have access to the kind of chemistry that will capture those minerals from those places, you can get all the food you need. And the warm temperatures are not only defending you, they're also a supply of energy that means you don't have to warm yourself up. You can have warm water in which to grow, which can accelerate your growth rate. So you can grow really very large because you have lots of things to eat and you've got lots of things to use to grow very large, and you're not going to get eaten. So these organisms do this because they have evolved to. They have tissues and chemicals in them that enable them to operate in those sorts of harsh environments. Just as we were saying, at the bottom of the ocean, there are creatures that are very happy living there because they have evolved structures of their proteins and molecules to stabilize their proteins against those the effects of those very high pressures. So there are organisms that have evolved particular proteins and body biochemistries that are optimized for those extreme temperatures. The reason we can't do that is because as warm-blooded creatures, we rigidly control our body temperature, and we have evolved for all of our enzymes and our biochemical systems to operate at an optimum, an ideal temperature centered on our human body temperature, about 37 degrees C. And as soon as you move your enzymes either below or above that temperature, their efficiency drops off until you get to a point where you get so hot that the enzyme completely destroys itself and becomes denatured. Well, it's perfectly possible to evolve enzymes which don't denature because they use very rigid cross-linked structures that make them much more robust, and they can tolerate these extremely high temperatures, but they're really, really inefficient at low temperatures. So if you took those organisms away from their hot house that they live in, they would be dead in a fraction of a second, in the same way that if you put you there, you would cook. So it's all about what these animals have evolved to tolerate and what they need in order to survive.
So there we go, Solly. You cook them in cold water and then you can add them to your paella. Dr. Smith, does the doctor's Antarctica answer mean global warming is a myth?
Well, the answer is no. Global warming is definitely not a myth, and it's been going on for billions of years. We can trace back through various records of isotope records, coral records, ice records, the pattern of global temperature change. And we've got very good records going back millions of years of the Earth having ice ages and warm periods. If you wound the clock back about 30 million years to something called the Eocene-Oligocene boundary, the Earth was so warm that we had no polar ice caps at all. The ice completely melted in the north and the south, and then it came back again. The Earth has gone through periodic cycles of warming and cooling throughout its 4,500 million year existence. And there are various reasons for that. One of them is that the planet wobbles on its axis a bit, and its orbit around the sun is not perfectly fixed. The sun changes its activity a bit with sunspot cycles that go over a sort of roughly 10 years cycle. And this all affects the amount of energy coming into the Earth, and that affects in turn how icy the Earth is, and that affects in turn how much energy we absorb from the sun. Superimposed on that are things like geological effects that make mountains, and if you make mountains, you pull CO2 out of the atmosphere, and that has the effect of lowering temperature. You have volcanoes going off, and that has the effect of injecting huge amounts of CO2 into the atmosphere and other gases and sulfate particles, which they also affect the temperatures. So all these things have over billions of years had a profound impact on the climate and on the temperature of the planet. What's different now is that we're into an era of man-made global warming. This is not a natural cycle. We know this because if we look at the pattern of how Earth's temperature has changed over the thousands to billions of years, you can see that there are certain things that always change in synchrony. This time, we should be going into, by this point, an ice age. The Earth should be cooling down. The Earth is getting warmer. And the thing that has changed and is out of sync is the amount of CO2 in the atmosphere. So we suspect that the trillion tons or so of CO2 that we've put into the atmosphere in the last couple of hundred years, which is what we have done, trillion tons, this is having a profound effect on absorbing and retaining more heat reaching the planet from the sun. So less is going back out into space than it should. So you're adding to the Earth's overall energy, and therefore you're increasing the temperature of the planet by a small amount each year. And we haven't seen a dramatic effect yet, although some people would argue that the effects we've already seen are dramatic because the Earth is well buffered. A lot of that energy is going into oceans, it's going into other places which are soaking it up. But the buffering capacity of those systems can only go so far before we begin to see more radical temperature departures. And that's what scientists are very keen that we're aware of and that we try and stop.
Our last question for today. Hi, Dr. Smith. I recently turned 50. And in the last couple of weeks, I've been having issues with dairy products. Never had any issues in the past. Is it possible to become lactose intolerant later in life? Anwar in Claremont with that question.
It's certainly possible that we can develop new allergies as we get older. It's a myth that you only get allergies when you're little and you grow out of them. I spoke to an allergy specialist at my hospital, Addenbrooke's, called Pamela Ewan, a couple of years ago, and put that very question to her. Do you see patients in your clinic who are older and get allergies as they're older? Yes, she said that absolutely can happen. You can listen to that as a podcast on The Naked Scientist if you want. But to lactose intolerance specifically, one of the reasons that we do become more intolerant of some foods as we get older is because as we age, our microbiome, the assemblage of microorganisms living in our guts, changes. And a lot of these microbes do important metabolic jobs for us without us even realizing. They're lending us their biochemistry to break down things in our diet that would otherwise poison us, be bad for us, or they release nutrients that would otherwise be unavailable to us. But as we age, that spectrum does change a bit, and so you can find that you gain some microbes and you lose others. The relative proportions of the populations of the microbes does begin to shift as we get older, most marked after the 60s, but it can begin to drift as we get into our sixth decade, and that may be having an effect on upsetting the biochemical apple cart in the intestine, and that might be one of the reasons why that's happening. Although it's very important, if you do have a change in bowel habit and it's abrupt and it's out of keeping and out of sync for you, you must get that investigated because there are other reasons why that might be happening.
As always, we thank you for your time. Dr. Chris Smith, the Naked Scientist, Chair of Science at the University of Cambridge. He answers our questions on a Friday morning.